Hey folks, welcome back to Welding Wednesday. We are going to go through our part 2 of our GMAW now. Quick review last week, or last time I listened. We just went through kind of like machinery, the equipment, how GMAW was developed, that sort of thing. So this week, we are going to do transfer modes, technique for welding, and then troubleshooting. So starting with our transfer methods, transfer mode, transfer method, kind of interchangeable term. So what is that? It's the way that the molten metal moves from the consumable electrode to the weld pool. So right here, we can see in this GIF, right there, this is the transfer mode or transfer method. This will be pulse. So we can see power on, power off, like pulse. And then you can see the little droplet getting put into your weld pool. So what does the transfer mode determine? It determines your characteristics of your arc, what the heat input is on the piece you're welding, and spatter levels. Some things that influence the transfer mode is your voltage, your shielding gas composition, and your wire feed speed. This is a very common mistake people make, and we're going to talk about it more here shortly. And then what the transfer modes can do is they can optimize your performance, whether, based on the material thickness you're welding, what position you're welding in, and what application the final item will be used for. So the most common transfer mode out there in the world is probably short circuit, as far as what most people use. Industry-wise, maybe not, but when you consider the part of industry that uses it, plus home hobbyists, people who have, a welder in their garage, that sort of thing, short circuit's where it's at. So short circuit is where the wire electrode makes contact with the workpiece, causing a short circuit. We can think about it kind of different than, I'm going to do a great drawing up here. So like if we have, this is our stick electrode, we know that we establish an arc, and then we have like this gap where our arc is. That's where the heat's melted, or the heat goes up, melts the filler and the base material, creates your weld. With the short circuit, so here's my weld nozzle, there is a wire, you're actually making direct contact with the welding surface, and then that's causing a short circuit. We're going to see shortly in a video how it goes ahead and actually propels material into the weld pool. What are some pros of short circuit? Low heat input, so great for thin materials, can be used in all positions, great for closing gaps. So if you have like an open root, depending on like what you're doing, sometimes they'll do a short circuit open root to weld that up and then fill it up using another type of process, spray, pulse, even 7 to 18 stick sometimes. And then it also works with 100% CO2, which has made it very cost effective traditionally. Currently, we do have some issues with CO2 supply, but traditionally more cost effective. Some cons: low heat input, ideal for thinner materials, which means limited penetration. So I know D11 structural steel, it says that you're not supposed to use it above like, I don't know, I think it's like 3/16 or something like that, but it's very limited. Even when you do like joint prep, so let's say you're welding a bigger joint and you put a big groove in there and you're going to do multi-pass, it just doesn't have the energy to penetrate and fuse the same way different transfer methods have. So you just want to use it on thin stuff. Again, potential lack of fusion authentic materials, just said that. And then you do need a higher quality of skill, or a higher skill to maintain quality consistent welds, because usually there's a lot of movement involved, like to be able to get that weld in there. You gotta do some decent movement, which we'll talk about later. So this is what's happening when you're actually doing a short circuit weld. So you have the weld your filler comes, makes contact with the plate and the weld pool. It heats up. It's heating up, causes like it's almost like an explosion because there's so much energy. It pushes your molten metal down into the pool. Then your wire continues to come out, makes contact again, and then just repeats the cycle. So here, can we play this? Ooh, I think we might be able to. So this is a video from Canadian Center for Welding and Joining. They do a great job. So let's see if we can get this playing here. There we go. Nice. So 70S-6 electrode, 045, 20 volts we can see here. So we have our, trying to draw on this video, but it's not working. But we can see that we have our little electrode going down into the pool. As it gets close to the pool, make contact right there, creates a short circuit. You're building up a bunch of heat where there's resistance, and then it's almost like a little explosion, like that. And so that projects your filler down into your weld pool, and then the process just repeats over and over again. So like this is, I believe, 3,000 frames per second. So that should be able to tell you like how much this, like how fast this goes. You know, it's really fast, and you're doing it thousands of times a minute. This little short circuit. That's where we get the noise of like the kind of like a steady like crackling is, you know, this process going over and over again. All right. Next one we have is globular. So globular is large, irregular molten metal droplets, and they transfer across the arc due to gravity. There's more energy than in short circuit, but it's less controlled. Globular is not used a ton, as far as I can tell, out in the world currently. Some pros of it are you get more deposition in short circuit. You can use it for thicker materials. Some cons are high spatter, difficulty used precisely. You can only do it in flat or horizontal because you have to depend on gravity to go ahead and get those drops to fall. And you can create an inconsistent bead appearance. So previously we said that you have to go ahead and you have to change shielding gas, voltage, wire feed speed to go ahead and change transfer method. So in this case, to go from short circuit to globular, we're going to turn up our power settings. When we go from like this to spray, which we'll do shortly, then we have to change our shielding gas composition as well. One thing I found is some people will be in like globular and think they're doing spray, and vice versa. So I want to make sure that we really understand we have to change multiple things in our setup to be able to go ahead and actually change our transfer method. So if we look at just globular right now, here is another video from the Canadian Center for Welding and Joining. So similar to short circuit, again, 3,000 frames per second, I believe, minute. Regardless, 3,000 is the rate. But we're melting. You can see it's a big blob here. It's not touching the weld pool like it was with the short circuit. It gets to be such a size that it breaks off and goes into weld pool. You can see how uncontrolled this is. You know, you're relying on gravity to get the metal where it needs to be. So you can see how once this like bubble gets bigger, it's moving all over the place. You know, it's shooting off like spatter, and then it gets to such a size where it's able to overcome gravity and then fall off. But you can see where it'd be very difficult to get like consistent welding and also all that spatter. So here we go again, just falling right in there. All right, next one is spray. So I said short circuit might be most used like overall, but in industry, there's a ton of spray and then a ton of pulse, which is kind of like a form spray. So spray is when we have a continuous stream of fine, uniform metal droplets. You have to have high voltage and argon-rich shielding gas. So at least 80% argon. Usually people do like a 90-10 mix, something in that world. Some pros of spray: high deposition, so we're putting down a ton of metal, deeper penetration for thicker stuff because we have so much energy. You get a very smooth and consistent bead with minimal spatter. You get strong fusion, excellent appearance. I think spray welds look great when you do them well. And you can use it in high-speed welding applications. I know a lot of like cobots automation will use spray or a version of spray with like pulse. The cons are tons of heat, so it can cause distortion. You can't do it out of position because you need gravity to help get those droplets where they need to be. And also it's just so hot, it can't like coalesce fast enough. So it kind of just drops out. You'll burn through thinner materials for sure. And then you have more expense usually because you have more argon in your mix. So when I was saying previous with the globular, how some people think that they might be in spray, but they're not. What'll happen is people will be in like short circuit and they're like, okay, to go to spray, I'm going to crank up my wire feed speed and crank up my voltage. Well, what that gives you is into like globular. So you're doing like globular, or you could even say like short circuit, just at super high energy. It's not until you get over 80% argon, you're going to get into spray. So that 75-25 that most people have for like short circuit, if you keep that and you just crank up everything else, you are still not going to get to spray. You need to increase the argon in your gas. So just really want to make sure that's clear, because I see that as a mistake people make all the time. They'll stay there in spray. And so I'll like look, and if they have a 75-25 cylinder set up, you're not doing spray. Spray is really cool though, I think, because when you do it, it does come out like, if this is our nozzle and there's our filler, it comes out like in a little fan shape almost. And it is kind of like spray painting. You're just kind of spraying it into the joint. It's very high heat input, so you do have to be careful. If you're going to be doing a long time, you're going to need probably like a water-cooled torch, so you're not going to melt any torch component. I've seen people get too close when they're welding and either melt like their cover lens or part of their helmet. People have told me that it can get so hot that it can crack your filter lens if you're too close. This is where you'd want to have like extra heat pads and things like that for your arm that's closest to the welding, that sort of thing. So tons and tons and tons of energy are going to be used. Also, definitely got to make sure you change your filter lens, all that sort of thing. So let's look at some spray. Yep. So we can see some of the settings here. 400 inches per minute wire feed speed, and I think it's at like 30 something volts, so lots of energy. And we can see that kind of like cone shape I was talking about, and just these little droplets coming off. So very little spatter. You can see it's very controlled. Tons and tons of energy. All right, and the last one is going to be pulse. So pulse is a variation of spray. So what you're doing is you're actually turning the electrical current on and off. And what that does is that helps to reduce heat and allows you to do basically like spray in or do spray out of position. So not just in the flat or in the horizontal. So some pros: lower heat input, especially compared to traditional spray. And then it allows for that welding positions I talked about. With cons: higher initial equipment setup, cost, more complex setup. I will say, like, a lot more machines nowadays are like integrating pulse programs in them, but just because your machine has a program for pulse doesn't always mean you can do pulse. So for example, older millers, wire feeds, depending on what type you had, would have like a pulse setting, but you wouldn't be able to actually use pulse unless you got an extra device called like an Omni Pulse, I think it was called. And that would help like the power source and the wire feeder talk to each other or something to that effect to actually make the pulse happen. So more and more it's being integrated. The machines that can do pulse are going to be more expensive, but that's something to double check. Just because it says pulse, does that mean it can do it as it's set up, or do we need to add some additional stuff to get it to work? All right, and let's look at some pulse welding here. So again, we have a 90-10 mix, it looks like. We're going to be 250 inches per minute, so that's less than with our spray. And we can see, so we have arc on, it creates your drop. So arc on, drop, arc off. And you can see that the drops are way more consistent than they were with spray and way more regular. And so when we got the arc on, we are melting our stuff. As it turns off, it's allowing that metal in the weld pool just to have a little bit of time to firm up before the next drop comes in. This is super useful for that out of position welding, because then we can get the results of the spray, which is increased deposition and penetration, but we can do it out of position. The heat input is less, so you can really help to prevent some warping. And then the other cool thing, which I've learned recently, is that pulse is also a great option if you need to reduce like your fumes. So usually if you have like too many fumes, OSHA comes in, they'll do an air test. They're like, hey, your manganese is too high, something like that. You could do things like try to switch your filler material to something like lower manganese. That's just our example. Or you can go ahead and get a better like ventilation system for the whole shop, or you can go ahead and like get pappers or something for the welders. But in this case, you can also switch to pulse. So pulse greatly reduces the fumes, because you're just not having as much heat heating everything up, and you're not having as much of like welding time on. So it's a pretty cool option to use. I think Lincoln has a thing that they've come out with called like pulse on pulse, which is an even more advanced way of controlling these droplets, but also reducing fumes. All right, quick comparison chart of these four transfer methods. So short circuit, low heat input, globular medium high, spray high, pulse medium high, spatter really low for things like pulse, pretty high for globular, penetration, deep penetration for spray, shallow for short circuit, globular and spray, flat horizontal, other two all positions, shielding gas, CO2 mixed gas. For spray and pulse, we're going to need above 80% argon. And then best for, so short circuit like thin metals, globular, heavier fabrication, spray, thick materials, and then pulse, thicker materials and thinner materials. You can do more precision. You can do structural welding with it, like we keep saying, out of position. So pulse is pretty awesome. It allows you to do a lot of stuff. All right, so second part of the day is about technique. So when you are welding, there's variables. And there's like 5 variables that kind of apply to each type of welding process. And in this case, for GMAW welding, these are the 5 variables that I have always kind of identified and then worked with students to adjust. So these are kind of the basis about how to use technique to get the results you want. So your 5 variables are power, travel speed, electrode extension, gun angle, and travel angle. Looking at this picture here, you can just see there's some changes in technique, and you can see the different appearance for the beads, different penetration profile, that sort of thing. So to start off with power, your voltage. So the higher voltage you have, more arc length, more fluid, less spatter in the weld. Lower voltage, smaller arc length, more instability. For bead shape and penetration, higher voltage, flatter, wider bead, shallower penetration. Lower voltage, narrower bead, more penetration. Approximate settings for your transfer modes. Now this depends on material thickness, size of your electrode, position you're going to be welding, all those sort of things. But approximately, your transfer mode for short circuit your voltage setting for short circuit should be about 16 to 22 volts. Your settings for globular about 22, 26, and then spray pulse about 26 to 35 volts. Next is travel speed. So travel speed is going to be controlled by your wire feed. So the wire feed speed, that's going to control the rate that the electrodes fed into the weld pool. Lower wire feed speed decreases arc length and more instability. For weld size and penetration, higher travel speed, wider and flatter bead with more penetration. Lower travel speed or lower wire feed speed is a narrow bead with less penetration. Transfer modes settings, again, these are approximate for the same reason I said before. But short circuit about 100 to 300 inches per minute, globular about 250 to 350, spray pulse about 350 to 500. I love this picture because it does a great job of showing like the differences with speed. So top one is pretty decent, and you really want to look at like how these crescents are shaped. So if we have like nice smooth crescents, we're going at like a smooth rate of speed, regular travel speed, right where I want to be. Any time you see a point, so you see these points down here, point means too fast. So if you're looking at your weld and you're seeing points, we're going too fast. We need to slow down. If you have a wide bead and we're not curling as much, it's more kind of like straight across, then C, kind of like C-shaped up on the top one, that's indicating too slow. So when you're welding, if you haven't done it before, when you're welding and you start to get like pretty proficient, you'll be able to read what's going on while you're doing it and adjust these variables. So like for instance, if I was welding and I start, I'm seeing that my bead has these points, I'm going to slow down, try to get it to what it's like up here. If I slow down too much and it gets wide, I'll speed up. Again, try to get up here the entire time. Another thing I wanted to point out is like the relationship between your wire feed speed and your voltage. So we see here that it says for wire feed speed, if we lower it, it's going to decrease your arc length and more instability. You might have remembered that from the previous slide. What's another thing you can do to change your arc length and more instability? Instead of lowering wire feed speed, increasing voltage will get the same type of effect. So when it comes to your voltage and your wire feed speed, it's all like a balance. So if you are having voltage that's too high, your choices are you can either decrease your voltage or increase your wire feed speed, depending on what will work best for you. So it took me a long time to figure that out, and still I struggle with it sometimes, but it's a balance between the two. So you always have kind of like two options on the machine to like adjust to get where you need to go. And it's either going to be changing your wire feed speed or your voltage. Your electrode extension, that's your stick out. Very important thing, it's the distance from the contact tube or tip to the arc. So a very common mistake I've seen people make is they think nozzle to work distance is contact tube to work distance. They're different. So here we see two different styles of guns. One of them has your contact tube just slightly proud of your nozzle. So this from here to here is your contact tube to work distance. This one has a nozzle that's back, a contact tube that's back in the nozzle. So from here to here is the contact tube to work distance, but make a note, the nozzle's the same as far as the distance. So don't go off your nozzle. We have to know where our contact tube is, and that is how we determine our electrode extension. So if you have a longer extension, that's going to increase resistance. That means higher heat is going into the wire, less is going into the weld pool. Shorter extension reduces resistance, so there's going to be less heat in the wire, more in the weld pool. Yep. Makes sense? So if your wire is melting too fast, what do? Some people would be like, okay, I'm going to pull back for less heat. But in reality, it's the opposite. You shorten that electrode extension so that you're going to get more heat in the pool instead of in the fire. For your different transfer modes, approximate settings for your electrode extension, short circuits usually about 1/4 to 1/2 inch, globular about 1/2 to 3/4, spray balls about 1/2 to 1 inch. Work angle. So work angle is going to be the angle of your gun in relation to the work. So if we look at like a T-joint, this would be like your front view of your T-joint. Here's a side view. You can see here, this is travel angle. So travel angle, which we'll talk about in 1 second, that's the direction or the angle of your torch in relation to the path you're moving. Work angle is in relation to the work itself. So you can see here, for this T-joint, our work angle would be whatever our angle is between this vertical member and our horizontal member. So that's something you adjust based on trying to get like an even amount of weld metal on each piece of base material. If you're doing like, if you're welding things with like differing thicknesses, you're going to focus on one or the other more or less, depending on how much penetration you need, that sort of thing. And then for travel angle, this is going to be, again, in the direction of travel. So for short circuit, we can do either a forehand, which is also known as a push, or you can do a backhand, which is also known as drag, or pull. And these give different results. So a push, you're going to have a shallower bead, and then a wider contour. Drag, you're going to have deeper penetration and higher bead. So I said earlier that short circuit is not very good for penetration, not very good for thicker things. But let's say you are welding something that's like 1/4 inch. So we're getting to like the max we want to do, like with short circuit. One thing you can do to help increase your chances is, instead of pushing, you can choose to drag or pull, because when you drag or pull, you're going to get that deeper penetration. Likewise, let's say we're doing something very thin, and you want to use short circuit. Okay, we'll go ahead and push, because that's going to give us a lot shallower penetration. Ideally, in a perfect world, and we'll see why shortly, you want it straight up and down. But we can't really do it straight up and down because we won't be able to see what we're doing, and it's just mechanically not very possible. So we are going to choose to do push and or drag. One thing you'll need to do a lot also with short circuit, as I said, is manipulation. So you can't really just drag it or push it without any movement. Now spray, totally can. You can drag spray, no problem. Straight line, you're going to be great. But since the wire is like a lot smaller than something like a stick, you're going to need to be able to manipulate that gun to be able to make the joint size you want. Also, depending on what position you're welding, manipulation is absolutely necessary. So for me, I was always kind of taught the curlicue, so that's what I do. Also known as cursed E's, like that. But there's many different styles of doing this. One thing for like, if you wanted to do vertical up, you have to do some sort of movement. So usually it's either going to be like a triangle or a square weave. And that's going to allow you to like fill the toes of the weld and keep the middle part as flat as possible. Because if you do other types of manipulation, you'll get a really high crown in the middle and then toes that are like underfilled. And it doesn't look very good. So I'll say, in my opinion, vertical up, short circuit is one of the more difficult like welds you could ever do. That's why you do, you keep it very thin, and you can do vertical down. But if it's above like 1/8 of an inch and you do a vertical down, man, you're going to really have issues with lack of fusion. So it's just something to keep in mind. All right, last section of this session is troubleshooting. So when I have somebody who gets in touch with me and is like, hey, this is the issue, what I like to do to keep myself organized is I start at the work and I move backwards through the system. So let's say like let's say this is our work. There's our welding gun. It's a pretty great picture, I know. And then you have your power source, and we'll say over here is your gas. So again, beautiful picture. So work, power source, gas. So I'm going to look at two main issues and how we can kind of figure out what they are through troubleshooting. So first we'll look at porosity. So porosity is gas pockets or voids that are trapped in the weld metal. What can cause it is contaminants like dirty wire, base metal, improper gas mix, your shielding gas if you don't have the right flow rate, leaking hoses or connections, winds or drafts, and then technique that can cause it. It's excessive electrode extension if you weld over your previous speeds without cleaning, or extreme angles or too fast travel speed. So, got porosity. Somebody's like, hey, I got porosity. I've tried all sorts of stuff. It's not, it's still showing up. What do I do? So this is where, again, I'm going to start at the work and move backwards. So if I'm at the work, okay, is there a breeze? Let's start right there. Breezes of 3 miles per hour or more can blow away that shielding gas pretty easily. So, is there a breeze? No. Okay, move on to the next thing. Is our wire or base metal dirty? Yes, okay, that could be it. No. Keep moving on. Okay, now we're getting to the gun. So the gun, we could have an issue with shielding gas flow, which we're going to see pictures here shortly of what that would look like. But basically, you can get spatter and everything stuck up in the nozzle, so we're not getting the right flow. In addition, are our settings correct? So you should have 30, 35 CFH for almost everything. People think that, more gas equals better welding, but it's actually the opposite. So if you have too low of a flow, you're not going to get enough shielding to protect from the atmosphere. Too high, and you actually create turbulence around the weld zone. And this turbulence is known as the Venturi effect. You see it more with GTAW, but what actually happens is that it draws in outside atmosphere. So let's say this is our weld gun. Here's our plate. If this is too high, this gas coming out, it actually hits the surface of the base metal and then goes ahead and kind of curls around. That's the turbulence. And so what will happen is it'll start pulling in atmosphere from the outside. And so you're actually pulling in atmosphere and putting it down into the weld. So I like to tell people, if you have too high of flow settings for your shielding gas, at best, the best thing that will happen is that you're going to waste shielding gas. The worst thing that will happen is this right here, where you're actually making porosity much more prevalent by having that high flow rate. And then some people might be who don't know better, they might be oh, I don't have enough coverage. I need to do it even more. So you just keep turning up your gas, your flow rate, and the problem just keeps getting worse. Okay, so we work back through here. We look at our gun. All our parts are good. Okay, no. We keep moving backwards. Okay, do we have any sort of holes in our lines or connections? Do we have a good connection to our power source? Everything looks good. Okay, keep working back through the system. Do we have good connections with our cylinder? Back here, look at the cylinder. Do we have our regulators set properly? All that sort of stuff. Oh, look. My valve's not open on my cylinder. That's what it was. So we walked all the way through the line to get to the valve, but hey, we found out what the porosity was in this case. For your gas coverage and angles, when we were talking about push or pull, angle is important. I said, ideally, we want it straight up and down because of this right here. That's the optimal gas coverage, but we can't have that because for a multitude of reasons. So we need to minimize our angles. A lot of things with welding that I've found is you're looking for the minimum effective dose. So your angle you want is the least amount of angle that allows you to do the job. So here, off of center, this much can allow us to do the job and still maintains a decent gas coverage. But the more we increase this angle, we see this gas coverage get smaller and smaller and smaller. And so you get to the point where you have too much angle. That's going to really affect the penetration and also really affect the shielding of the gas. Another thing I spoke about with the porosity is a restricted nozzle. So this is all that nasty old spatter that gets stuck up in there. And you can see very easily you're blocking airflow of material. So everyone who is doing any MIG welding should have these handy little things called welpers, which stand for welding pliers. They are specifically designed to help with MIG welding. And one of the things you do is you pop that nozzle off, you stick the two, I guess, tines, I don't know what exact word would be, of the welper into that nozzle, spin it around a few times, knock all this junk off, and then you're good to go. You're not going to have that restricted airflow. Another thing that can cause that porosity is the bad connections we talked about. So we see here the setup for internal drive roll unit. What I wanted to key in on here is last week we talked about these parts. So we have our rollers, tensioner, here's our wire guide, but then right here is where we hook up our gun cable. So you can see right here too. So this one, no gun cable is hooked up. This, you can see the gun cable's hooked up so many times. And this is pretty embarrassing for people. But I don't think it should be embarrassing. It's just a thing that's common to overlook. So many times porosity is going to be caused by not seating this completely into the drive roll assembly. So what will happen is there'll be a little gap and you're going to be drawing in atmosphere right there into the gun cable. Porosity. So, I had somebody who's hey, getting porosity, don't know what to do, kind of walk them through verbally what I've shown you. And they're like, no. And I'm like, well, bring it in, I'll take a look at it. So they brought it in, I popped open the cover and I looked, and that's what it was, is it wasn't seated properly. So you have the screw, you go ahead and unscrew it, you go ahead and seat it, push it in, screw it down, good to go. So that's a major thing to pay attention to. The other big troubleshooting besides porosity would be something like inconsistent wire feed or arcing. So what can happen with this? We see a good example of bird nesting here, but you can have too tight of roller tension. We talked about that last time. You can crush your wire. Too loose, it's not going to feed consistently. You can get the bird nesting. You can have the wrong roller type, so it's not grabbing the wire properly. Your contact tube can be overheated or misshaped, and so you're not getting a consistent arc, or you get burned back. So you're having too high a voltage or too low a wire feed speed, so all that wire is burning back to your contact tip instead of going into your weld, and that's that balance. So here we can see different sized rollers, too small, too tight tension, we can go ahead and crush that wire, or if it's too large, you're not going to get a grip on it at all. Then it won't flow through your cable. For the contact tube itself, so spoke before about the electricity is just added at the very end, and at the very, very end is a circular hole. Over time, the wear on that will become an oval. And when that happens, you're not going to get consistent electrical flow because there will be more resistance, and that can lead to actually arcing inside on the wire. So this picture over here is a wire that's been magnified, and you can see where it's been arced inside the contact tube and the wire. So not great, because you're going to be losing a lot of power for resistance, not getting consistent feed. Something to kind of think about and watch out for, you might not know, but the actual filler for GMAW has in particular what's called cast and helix. So it's wound onto the spools in a very particular way. When you're loading and unloading, if you're not making sure it doesn't become unwound, what can happen is, because there is some tension in that, it can become unwound a little bit. When it becomes unwound, it can lose the cast and the helix, or basically the way it was wrapped. And it's designed that way so that it will feed through your liner consistently and wear the entire liner in a consistent way, not just in one place. and so you get consistent contact for electricity in the tip. So that's another thing that can happen. It's not probably going to affect it majorly, but if you allow that spool to unroll at all and then you try to wrap it back up, it can negatively affect the ability and the quality of the weld. And then finally, contact tubes here. I believe this is close to finally. Talked about them overheating. This happens all the time. They get overheated. People mess around with them. They get all bent up. Or you get that burn back where you're going to get that wire almost fusing itself to the end of the copper contact tube. So if you see this, you need to either turn down your voltage or turn up your wire feed speed. A lot of times you'll get this and now it's trash. You can't go ahead and get that off. You got to put on a new contact tip. So just something to keep in mind. Depending on the type of contact tips, they're like $2 a piece. That can add up really fast if you are if you're getting a lot of this. So adjust those settings. All right, and then finally here we have a slide that shows a bit of the voltage wire feed speed balance I was talking about and how it can affect the appearance of the weld and your penetration. So let's say wire feed speed. So this would be lower on this end. There we go, lower on this end and higher on this end. And then it would be the opposite for voltage. So this would be like higher voltage on this end, lower voltage on that end, as far as like the balance between the two. And you can see how it can really affect what the bead looks like and your penetration profile. So you can see here, like lower wire feed speed. It's going to be like super like ropey, kind of, not really ropey, but like you're not going to get the right type of fusion penetration. Very smooth over here. You can see less penetration, more penetration, that sort of thing. Great. Okay, so that should finish this up for this session. As always, here is a selection of the resources I used. If you have any questions, concerns, comments, as always, please let me know. Really appreciate you folks tuning in. This is the longest one so far. Hopefully this will be the longest one, period. Every other one should be a bit shorter. So really appreciate your time, and yeah, have a great rest of your day. All right, see ya. Bye.